Hello everyone. So here we are going with that second experiment of ECD lab. The name of experiment number 2 is layout, physical verification, placement and route for design, static timing analysis, parametric analysis of two input NAND and NOR gate. So before going for the design of NAND and NOR gate, first we have to understand how we can design using CMOS design or CMOS logic design. So let's go with this. So before going with that, the actual CMOS logic design, we should understand the transistor as a switch. Basically here we are looking for MOSFET. We are having a NMOS and PMOS. It is symbolically a representation of your NMOS and PMOS. It has the three terminals: source, drain and gate, and the fourth terminals is body. Right now it is not shown. It means it is integrated with source. In the same case for your PMOS, source, gate, drain, and the fourth terminal is body, which is integrated with source. What happened if gate equals to 0 for NMOS? So that transistor is off. That means drain to source is isolated. When your gate equals to 1, the transistor is on. When gate equals to 0, what about your PMOS? It is on. When gate equals to 1, your PMOS is off. So basically here we have to remember, in case of your digital, when your gate equals to 0, your PMOS is on. When gate equals to 1, your NMOS is on, and vice versa. In VLSI, especially in digital VLSI, if you are looking for CMOS logic circuit, so it can be divided in the two way, that's static and dynamic. The static has four types: complementary logic, or also you can say CMOS logic, pseudo NMOS, pass transistor logic, transmission gate logic. In dynamic, we are having two, the dynamic and dominant logic. Here we are going for that complementary logic to design NAND and NOR gate. So before going for that, the NAND and NOR gate, we should understand how your CMOS logic is made. So basically CMOS logic is having a pull-up network, that is a PMOS, and pull-down network. It is the combination of your pull-up network, that is a PMOS, and NMOS, where the gate inputs are common. The source of pull-up network or the PMOS is connected with your VDD, whereas the sources of your NMOS is connected with ground. The output is taken from their common drain. So let's take the example of inverter that already we have seen in that experiment number 1 session. So if we are having that inverter, so here you can find it is the combination of your one PMOS at upper side, one NMOS at lower side. Their gate input is common, the drain connection is here, and we are taking from their common drain connections. Source of PMOS is connected with VDD, source of NMOS is connected with ground. So let's go with that. Again, we should have that two important nodes for CMOS circuit connection, that series or parallel. In Boolean expressions, we are having two types of operations. The first one is that is a dot operation, and second we are having that plus operation. Dot operations generally we are saying about AND gate, plus operation generally we are saying about that OR gate. But in complementary logic circuit or CMOS logic circuits, always we are getting inverted outputs. So when we are having a dot operations, NMOS, number of NMOS are connected in series. For dot operation, your PMOS should be connected in parallel. For plus operation, NMOS should be connected in parallel. For plus operation, that PMOS should be connected in series. So we should note this first note, and the second important note is that the number of inputs for any Boolean expression equals to number of PMOS equals to number of NMOS. Sorry, it's something, okay, that is number of NMOS. The number of inputs equals to number of PMOS equals to number of NMOS. Hence, total number of MOSFETs are 2 into number of inputs. So let go directly with NAND CMOS NAND gate. So this is simply of your the symbol of NAND gate. It has the two inputs A, B, and the output is Y. How we can write their Boolean expressions? Y equals to A dot B bar. Now look at here. The number of inputs are 2. So that's why we are going to use here the 2 PMOS and 2 NMOS. As there is a dot operation, so for dot operation your PMOS should be connected in parallel. For dot operation your NMOS should be connected in series. This is simply a truth table of your NAND gate. When both the inputs are 1 1, the output is 0, remaining it is 1. In the same way, what about your NOR gate? A and B are the inputs where output is Y. Y can be written as A plus B bar. So as there is a plus operation, so for plus operation your PMOS should be connected in series and NMOS should be connected in parallel. As two inputs, so that's why 2 PMOS and 2 NMOS, where the gate inputs are common as there is A of this P1 and N1, B is for your P2 and N2. The truth table of your NOR gate, the output becomes 1 when A and B are 0 0 and for remaining these are 0. So with respect to this design we directly go with that the schematic. So in Micrometer we are having that one tool, that digital schematics. So using this tool we can design that NAND gate and NOR gate as well as we can check their functionality. So initially we are going for that NAND gate first and then we are going for NOR gate. So for NAND gate we are having the expression is Y equals to A dot B bar, and that's why we need that two inputs. For two inputs we need two PMOS and two NMOS. As there is a dot operation, so for NAND gate these two PMOS should be connected in parallel. For dot operation we can flip, then we need two NMOS, first NMOS, second NMOS, this should be connected in series. We can flip it for appropriate input connection you can say. So by wire we just do the connection. First PMOS, second PMOS is connected in parallel. The drain connection is connected with your first NMOS. First NMOS connected in series of second NMOS. Inputs are common, so we are taking as A. It is for your B. Then for VDD, source of PMOS is connected for VDD. Source of NMOS is connected for your ground. So we do that ground connection for your NMOS source. We do VDD for PMOS source. Here we use the button for the input. This is A. Here we use that second button for second input, that B. Do the connection using wire. Here we can change their name as the input is A. We can change second input as a B. For output observations we are taking that LED. We can check the output name as Y. So it is simply of your NAND gate. We can observe their output by using simulation. So when it is 0 0, the output is 1. When it is 0 1, the output is 1. When it is 1 0, the output is 1. and when it is 1 1 the output is 0. Now look for the MOSFET action. When it is 0 0 both PMOS is on, hence this LED get the supply from VDD. When it is 0 1, though second NMOS is on, but because of first NMOS it is isolated with ground, while the first PMOS is on, and hence LED will get that the path with VDD through that first PMOS. In the same way, for 1 0, here first PMOS is off but second PMOS is on, hence output will get supply VDD through that second PMOS. As input A is 1, so first NMOS is on but second NMOS is off because second input is 0. When both are 1 1, both PMOS are off where both NMOS are on, hence output is connected with ground, that's why that output becomes 0. We can check their waveforms, timing diagrams. So it is simply your timing diagrams. You can check their functionality. When both are 0 0 the output is 1. When 0 1 the output is 1. When 1 0 the output is 1. When both are 1 1 the output is 0. This is about your NAND gate. Let's assume this NAND gate as the output is y1 underscore NAND. We are going to simulate both NAND and NOR gate on the same screen or same platform here. So we are going for that NOR gate. So NOR gate is just the complement of your NAND gate. In NAND gate, both PMOS are connected in parallel and NMOS are connected in series. In NOR gate is having that y equals to A plus B bar. For plus operation, PMOS should be connected in series and NMOS should be connected in parallel. So we will take that two PMOS. The first PMOS, we are having a second PMOS. We make it flip for appropriate input connection. We will take that two NMOS. The first NMOS, we will have that second NMOS. And then we do the connection. Then source of NMOS is connected with ground. Source of PMOS is connected with VDD. Inputs are common, that is for your A. Here we are taking our second input, that is for B. If we are going to use the same buttons, so we can apply the same input to NOR gate also. So if we consider this of your B input, so we just do one thing. We are making that common input for NAND and NOR gate as the input B. And we will take that second input, that A, NMOS source connected with ground, PMOS source connected with VDD. So this is overall design of your NOR gate. It is NAND gate. So for output, we are taking the output at common drain. So we will take that another output. change their name as y2 underscore NOR. So let's do simulation once again. Check it. When both are 0 0, your NAND as well as NOR output is 1. When it is 0 1, NAND output is 1 but NOR output is 0. It just follow the truth table. When it is 1 0, NAND output is 1, NOR output is 0, and when both are 1 1, NAND output is 0 as well as that NOR output is also 0. So just follow the truth tables. You can check the timing diagrams. This is the timing diagrams. So when both are 0 0, both NAND and NOR are having that 1. When it is 0 1, NAND is 1, NOR is 0. When it is 1 0, NAND is 1, NOR is 0. And when both are 1 1, the NOR is 0 as well as that NAND is also 0. You can save this file. So we will take as experiment number 2, that is NAND NOR gate. So for NAND schematic, we can give here the name as NAND gate. And for NOR gate, you can write as NOR gate. Then this schematic will be used in layout when we are going that layout conditions. So when we take the printout for particular manual, so you can go with that monochrome color. You can run once again the simulations. You can find 0 0, then 0 1, then 1 0, and last one is 1 1. Timing diagrams. You can observe the timing diagrams, and you can just carry out this printout. So for printout, again we are going with that print screen. Open that paint, just copy it. You can save the file.